We're going to cover 1.5, scientific notation. So as I can write very large and very small numbers using scientific notation. So a compact way using base 10 to write very large or very small numbers in our vocabulary would be scientific notation. The next one there says numbers that do not contain exponents. That is going to be when a number is considered to be in standard form. So our everyday numbers. Okay. So then learn scientific notation. Scientific notation is a way of expressing a number as the product of a factor and an integer power of 10. When the number is positive, the factor must be greater than or equal to 1 and less than 10. For positive numbers written in scientific notation, a times 10 to the n, where a is greater than or equal to 1 but less than 10. So the number in front of the decimal has to be between the numbers of 1 and 9, and then it can have a string of numbers after the decimal. But that first number has to be between 1 and 9 is what this is saying. So they give two different examples of numbers written in scientific notation. Now they want us to go down here and circle each number that is written in scientific notation. So this first one, it has a 10 in front of our decimal, so that does not work because it has to be between 1 and 9 in the first part there. So 2 is between 1 and 9, and it has times 10 to some power, so this answer does work. The next one, our number in front is 9, which is between 1 and 9, and then it does have times 10 to some integer power, so this one is in scientific notation. The fourth one has a number that is 0. That's not between 1 and 9, so that one does not work. So it's only those middle two. So here it says if the exponent is blank, if it is positive, we will move the decimal to the right, and the number is going to be getting bigger. Okay, we'll be getting a big number. So like in this case, it has 1.365 times 10 to the 2. So positive means I move right, and my exponent tells me how many. So I moved it behind the 6. So this number is actually 136.5 because I moved that decimal place twice. If the exponent is negative, we will move the decimal place to the left, and our number will be getting smaller. So here it's saying that I'm going to move it left twice, and when you have a blank like this, you fill it in with a 0. You should always start these numbers out as 0 points, and then fill in what you had. So when we had a negative 2, we got 0.01365. So they want us to practice that with these next 6. So this first one here, it's a positive 4, so that tells me I'm moving right. So I rewrite my number, and then I move right what my exponent says. So it says 4, so 1, 2, 3, 4. In those blanks, we plug in zeros. So this becomes 53,400. So it's the same idea for this next one. It's a positive exponent, so we go right, and we're going right 5 times. So we have 9.931, and I count 5 times to the right. So 1, 2, 3, 4, 5. Fill in any blanks with zeros. So this one became 993,100. The next one wants us to go right 3 times. So we had 1.42. So that's 1, 2, 3. Plug in that 0. So this is 1,420 in standard form. The next 3 we have here are negative exponents. So I kind of blocked out that first one there. It's a negative 3. So we rewrite our number, 3.27. Since it's a negative, though, we're going to go left. So we go 1, 2, 3, fill in those zeros. So like I said up above, you always start with 0 point and then write the number you have there. So we had 0.0327. So that'd be our answer there. So then we had 6.02. It's a negative exponent, so we'll go left, and we go left 4 times. So 1, 2, 3, 4. Plug in those zeros. We always start with 0 point, and then we write what we had. So we had 0.000602. The next one has a negative exponent as well, so we're going to go left. It's 2.079. I go left twice. Fill in that blank with a 0. Always start with 0 point and then fill in my number. So 0.2079. So that is that number in standard form. So the next part is going to have us talk about technology. So this is mainly going to be if you use a handheld calculator, but if you use Desmos, I'll briefly talk about how to type it into Desmos. So over here, up at the top here, if you are using a handheld calculator, to specify scientific notation, handheld calculators use this capital E. So if your calculator says 8E11, what that means is 8 times 10, and then that number is the exponent. So it'd be to the power of 11. So all of these would be times 10. And then the part after E is your exponent. So in the 2.5e negative 12, that means that exponent is negative 12. For the 4e to the negative 7, that means our exponent is negative 7. Okay? So then it kind of talks you through how you type things in there. If you go to type it into Desmos, especially when we get into operations, you will want to make sure that you put parentheses around your scientific notation. So like this. You type your scientific notation in parentheses and then do whatever math you need to do to it. So like I have some examples pulled up here in Desmos. So like I showed me adding them. I made sure to type them in parentheses. And as you can see, one of them gave me an answer in scientific notation, one of them didn't. So if they give you one that's not, you have to convert it to scientific notation, which we'll talk about in 1.6. But this is how Desmos works with this, and this is the calculator that the Ohio State test uses. So now we're going to move on to this next part, which is when they give it to us in standard form, going and writing it into scientific. So it says, when writing a positive number in scientific notation, the sign of the exponent can be determined by examining the standard form of the number. If it is greater than or equal to 10, so if it's a really big number, it's going to be a positive exponent. If it's between 0 and 1, so a small number, it's going to be a negative exponent. So they gave us 2 examples here, and then they want us to use this to answer these next 4 questions. So if I look at 3,725,000, that's a big number. So I'm going to have a positive exponent. So then to figure out what this is going to be, our exponent always starts here in the back if it's not written, and then you move it. So if I move it, I go 1, 2, 3, 4, 5, 6. and I stop once I have one number in front of the decimal that is between 1 and 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are the only numbers that can be in front of that decimal, and it has to be just one singular number. You can't have like 37 or 372 or 3,725. It has to just be that 3. So when we go to write it in scientific notation, you write 3 point, and then you write every number after that until you hit that where it's continuously 0. So I would write 725. After that is 3 zeros, so we don't have to write it. So we write times 10, and then we said we moved it 6 times, so this would be to the 6th power. So that is this number in scientific notation. So it's going to be the same for this next one. So this next one, we have 8,785,000,000. So we're going to go ahead and move that decimal. They don't have it in the picture, so it's automatically after this last 0. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9. That 8 is the number that is in front of the decimal. That's between 1 and 9, so I know I'm done. So we would have 8.785. After this 5 is our string of zeros, so we don't write anything else. So then we write times 10, and then we moved it 9 times, so it would be to the 9th power. So the next one, if I look at those two, they are really small numbers because they start out with a 0 point. So they tell us where the decimal is, so we're going to go ahead and move that decimal so that we only have one number in front of our decimal that's between 1 and 9. Should be right here once I go after this 3. So we'd have 3.16 times 10. Since it was a really small number, we have a negative exponent, and then how many times we moved it is our exponent. So I didn't count this one out loud, but if we look, I have 4 little humps here, and that means I moved it 4 times. So it'd be to the negative 4th. This next one is also going to be negative because it's a small number. And I move my decimal so I only have one number in front of it that is bigger than 1 and 9, which is going to be this 5. Or is between 1 and 9, not bigger than. Between 1 and 9, which is this 5. So we get 5.24 times 10. We moved it once, so this would be to the negative 1st power. Okay. So these next few problems on this page are just us picking which measurement is appropriate, which there are a few typos, which I wasn't the one that made these notes. So, like that T shouldn't be there, and this E shouldn't be there. So it says, for example, when representing the distance from California to New York, should you use miles or inches? If you use inches, that's going to be a huge number. So the most appropriate size would be to use miles. Okay. So they want us to circle that in these next few. So the first one here says the time it takes to travel from Florida to Michigan. Should we use minutes or hours? Since this is a decent distance away, you would want to make sure that you use hours. The thickness of a penny. A penny is really thin, so you'd want to use millimeters. The length of a football field, it's already in yards when you look at a football field, so you'd want to use yards. The weight of a paperclip. Paperclips are really small, so you'd want to go with ounces. If you could walk at a rate of 2 meters per second, it would take you 1.92 times 10 to the 8th seconds to walk to the moon. Which one is more appropriate, to use 1.92 times 10 to the 8th seconds or 6.09 years? Well, it would make more sense to use 6.09 years because that's a smaller amount of time, like smaller number, not a smaller amount of time, a smaller number when you're talking about this. So we'll go ahead and go to this next page, and this is the last page for this section. So it says you can estimate very large or very small numbers by expressing them in scientific notation. Important, when we are estimating, we use this symbol. So we usually say about, and it's this two little squiggly lines. So they're almost like equal signs, but they got a little wavy. So here it says the population of Missouri is 6,063,589 people. Write an estimate in scientific notation for the population. So if I look at this number, that is very close to 6 million. So that's what I would round it to. I would say, okay, this is about 6 million people. So now they want us to write in scientific notation. So I would move that decimal until that number is between 1 and 9, so 6. So 6 times 10, and then when we look how far I moved it a total of 6 times. So that would be that number in scientific notation, or at least the approximate of that number. So it's about that. The diameter of an animal cell was measured at approximately 0.000635 centimeters. Write an estimation in scientific notation for the diameter. So when I look at this number is about 0.0006, because 35 would make us round down. So if we go to write this in scientific notation, we move that decimal until the first number in front of the decimal is between 1 and 9. So we go 1, 2, 3, 4. So we're going to have 6 times 10. It was a small number, so negative exponent, and I moved it 4 times. Okay. So this next part here, it says the table shows the approximate number of international visitors to the United States from several countries for July and August of a recent year. Which country has the greatest percent of change in the approximate number of visitors from July to August? So since they all have, like if you look at like Canada, Mexico, United Kingdom, Japan, they all have the same basis of 10. So times 10 to the 6th or 5th, depending on which one you're looking at. We're going to ignore those and just focus on the numbers in front of those times 10s. So for Canada here, we're going to go ahead and we're going to subtract, because percent of change is the difference divided by original times 100. So for Canada, we'd subtract our two values, so 2.43 minus 2.09. Now, since this is between the months of July and August, July would be our original. So this one is the original. So this is what we divide by. So we divide by 2.09. Okay? So if we go ahead and for Canada and we subtract these, this gets us 0.34 divided by 2.09. Which, if we divide that, we get about 0.162. So you can either multiply by 100, or if you know to move your decimal place twice, that's 16.2%. Okay? So that's what we have to do for all of these so that we can compare them. So next up, we'll do Mexico. So we'd be taking 1.63 minus 1.55. Divided by the original, which is 1.55. If I subtract those, I get 0.08 divided by 1.55, which comes out to be about 0.052, which is 5.2%. So out of these two, so far, Canada would be the greatest. So then we move on to the UK. This one is 4.9 minus 4.2 divided by the original of 4.2. If I subtract those, I get 0.7 divided by 4.2, which is about 0.167. So that would become 16.7%. So now UK has the greatest. So then we just need to do our final one here, which is Japan. So we'll go ahead and do Japan. We'd be taking 3.9 minus 3.05 over 3.05. Subtracting those gets me 0.85 divided by 3.05. If we divide those, we get about 27. Oh, we get about 0. Sorry. I already started converting it to a percent. When we divide that, we get about 0.279, which is 27.9%. So now I would look at the UK and Japan, because I said the UK was the greatest last time. And that would get me that our answer is Japan has the greatest, because we got a higher percent of change there. So that is it for the 1.5 notes.